Good morning, everyone. Hope everyone's having a wonderful day. So in this video, we'll be going through the 2020 VCAA physics exam paper. I'm hoping this video helps you guys better understand how a 50 study scorer, aka a full marker, approaches their actual exam. So I'm going to be actually doing this exam as if I was a VC student. So definitely will bring back a lot of memories, but hey, I'm doing this for you guys. So starting off with my game plan, I'm going to be using the reading time for just the short answer section, going through a couple of short answer questions, around 3 or maybe even 4 short answer questions. I like to prefer quality over quantity. Of course, there's no point in going through like 50 questions, but just like having a skim through them, because you're not going to remember everything, are you? So just focus your attention on just a handful of questions, and then when writing time starts, boom, I can quickly dash in and quickly get all those 4 questions over and done with, and then move on to the MCQ section, do all of them, and then I will start from question 1 in my short answer section. I know everything might seem a bit all over the place, but hopefully you guys can understand from this video why that is such an effective strategy. Alright, so let's get started. I have a timer on the top left, calculator on the top right, and so this will be me doing an actual exam. Alright, so reading time has started. Now we'll move on to the short answer. Let's try to find the hardest questions that we can possibly spot. Question 1's going to be pretty easy. Ooh, this seems like an interesting diagram, so let's try to understand this question. Alright, so an electron microscope uses a high precision electron velocity selector consisting of an electric field perpendicular to a magnetic field, blah blah blah. By the way, guys, obviously in an actual exam you won't be able to talk through a paper, but this is just for me trying to guide you guys through this. So what I'm saying out loud in this video is what I would actually be thinking in my head, and how I would actually process this question if I was doing the exam. Right, so electrons traveling at a required velocity. Alright, so we know that. Still don't understand the question just yet, so let's try to look at the diagram. Okay, so what do we have? This is from area of study 1, so I know that just from looking at the diagram. So we have electric fields, magnetic fields, so that stuff is all well and good. We have an electron, so I know that there's an electron, so I have to remember what was the what's the little trick to do with electrons when you're using a right hand palm rule. Imagine that you actually have a positive charge there, so your thumb is to the left, but we'll get to that later on. Okay, so I know that. Magnetic field, electric field, so I haven't really seen these before. Okay, so let's have a look. Okay, so the diagram seems a bit complicated. What is the first question asking you? Show that the velocity of an electron that travels through the aperture at point Y is given by this much. Okay, I can see from that equation that we have both the electric field and the magnetic fields influencing our velocity, right? So we're trying to show that the velocity is given by this equation. Okay, so both these fields, the magnetic and the electric field, are interacting with our electron. Okay, so, and I'm given 3 paths of these electrons as it's shown in the question stem. So which way is the electron moving, depending on the 3 paths that I have. Okay, right. Alright, so real quick, if I use my right hand palm rule with my fingers going into the page, my thumb pointing to the left, right? Of course, that's the key point there, and that means my palm will point downwards, so I can see from here that I would have a downwards magnetic force. Alright, and then I will also have an upwards electric force. Well, alright, so I can see from this diagram that it does make sense. The 2 forces balance out, and that's what this question is asking you about. So if I have the understanding, I can probably do part B as well, so we can move on to that. Part C, which points could electron travel? That. Which one could electron travel? All right, so yeah, so part B, if the electron speed was increased, now would the electrons be deflected upwards, or would they be deflected downwards, or will they not be deflected at all? Right, so that's what that part is about, and I'm sure I can determine that. I have confidence now that since I understand the scenario of the actual question, I would be able to answer that question as well. All right, so moving on. Oh, so we have a 4 marker here, so this will be interesting. All right, so looks at the Ionoscopic Connection Explorer, space where the satellite constructed to study the Earth's ionosphere was launched in 2019. Icon will study the link between space weather and the Earth's weather. So that's basically useless information there. Don't know about that. Okay, so this is important. Orbital altitude is 600 kilometers above this Earth's surface. All right, and we're assuming that's a circle orbit. So this keyword here, I know I'm not really meant to annotate since this is reading time, but just to show you guys, since it says specifically that we have a circle orbit, this should ultimately click in your mind that this is a circular motion question, and so you already have, or you should already have that content coming on the forefront of the mind. All right, so part A, calculate the orbital radius. Okay, so I should be able to do that because I know the radius of the Earth and the altitude. Part B, calculate the orbital period of the satellite. Okay, so let's just try to mentally see how this would work out. So just make a little mental plan here. All right, so what is this question about? Now, obviously, I don't have a super brain. I can't do equations in my head, right? Even despite what you guys might think, I definitely can't do that. So let's just lay out a general plan here. So this is a circular motions question and a gravitational field question. So we have 2 topics together, and so those 2 topics bring their own equations in the midst, right? So circular motion, we have the centripetal force equation, and then gravitational fields, we have the gravitational force equation, right? So we have centripetal force and the gravitational force equation. Now, ultimately, these questions are going to be based on the connection between the gravitational force and how it acts as a centripetal force, causing our satellite to move in a circular orbit. All right, so I have that laid out, and we asked to find the period. Now, I also know that the definition of period, well, that is equal to t is equal to 2 pi r over v, right? So I have 3 equations, right? And so that sort of gives me confidence that I could determine the period by finding some sort of connection between these 3 equations. All right, so that's all you really need to do in your reading time for a question like this. Okay, so this is a worded question. These are really good questions to go through in our reading time. Explain how the satellite maintains a stable circular orbit without the use of propulsion engine. So why can the satellite maintain a circular orbit even though there's no external force? Well, what is our answer? Going through our logic from part B, we know that we have a gravitational force. That's 1 point. But notice how there's 2 marks for part C, right? So there's 2 marks. So you can't just say, well, we have a gravitational force and how that's acting as a centripetal force, right? That's one point. But you also have to think about the second point, and this is where reading time is really, really valuable. And just having a think about this. So let's have a think about this. If the satellite was at any position around the Earth, could it orbit in a circular fashion, or does its position matter? So if we think about it, the satellite, so if there was a constant gravitational force, then yes, so the satellite would be in a circular orbit, of course. Okay, so let's think about something else. So a stable circular orbit. A stable circular orbit. So let's have a think about this. So what makes a circular orbit unstable? What if this satellite was launched at launched with an accelerating force, perhaps. Would that initial force impact the instability of the circular orbit? Maybe. Who knows? Right, so that's another thing that we can think about. Yeah, so I'm just thinking about this here, guys. I actually don't know the answer to this just by reading this. So that's another point that we can think about. Alright, so in my actual reading time, I could go through this in more in depth, but I've only gone through 2 questions so far, so I might skip over this question for now, and so we'll move on to the next question. Alright, so this is a familiar diagram to me, and hopefully this is a familiar diagram to you guys as well. This is a gravitational field graph, right? Of course, and what's the first thing that comes in your mind? Well, finding the area. So we definitely have to find the area for this question. Determine the change in the gravitational potential energy as the satellite arrives from the travels from the Earth's surface to the orbital altitude. So as the satellite is rising up from the surface of the Earth, what is the increase in its GPE, gravitational potential energy? Okay, so we know our initial height, which is 0, and we know our final height, which is 600. And so if I could find the area in this region, couldn't I, right? So that's something, but there's a lot of, you can say, tricks with this question, right? As there always are. We notice that we have kilometers here, right? So that's one thing we have to keep in mind. So you can't just find the area as it is. You have to convert the unit into meters. You can actually leave this as just altitude, by the way. You don't need to change this into radius, as we can see from the question. So you don't need to change your x-axis values. You don't need to turn them into radius values from the center, because ultimately we just care about the change in the area, right, or the change in the GPE, and that doesn't really matter. You're going to be adding a fixed constant for the radius of the Earth anyways to all of your x-axis values. That's not going to make any difference, is it? Alright, so I understood that. Alright, so let's move on. So we only have 4 minutes left, and I know I've been talking over, but I have done this practice exam as well in the past, so it sort of balances out, doesn't it? Alright, so we have a DC motor, and find the EMF. Oh no, this isn't a DC motor. My bad. This is a generator, right? So it's a DC generator, so that's interesting. Alright, so this seems like a familiar question, so we'll move on to any other questions that, okay, so this is an interesting scenario. I haven't seen this too much before. Okay, so we have 2 physics students holding a circle called a Y in a uniform magnetic field, and they are essentially stretching this coil outward. And this is going to be a change in magnetic flux, right? So this is that type of question. Alright, so will the magnetic flux through the coil increase or decrease, or stay the same as the students stretch out the coil? Well, we can see here just from the diagram that the number of magnetic field lines, or these crosses that are passing through the circle area, they decrease from figure 5a to figure 5b. So that should sort of click in your mind that, well, there is a decrease in the magnetic flux, right, and into the page as well. So that's the direction. There's 2 parts of this. So one is the type of change, and the other one is the direction of that change. So decreasing into the page, that is the change in magnetic flux. Alright, so looking at this diagram, you guys should hopefully realize, at least a couple of, after a couple of seconds of looking at the diagram, that this is an EMF question, right? A Lenz's law question. And what do you know? Part B is about Lenz's law. So we have to determine the direction of the current passing through the coil, right, that the ammeter is going to measure. And we do that with Lenz's law. So this mental connection should already be built up in your minds between current and Lenz's law. Whenever you see the term induced current, you're going to be applying Lenz's law. All right. So looking at this, I can do this in reading time real quick. You only have 90 seconds left. So the change in magnetic flux is into the page and it's decreasing into the page, so we need the induced flux to be out of the page to sort of oppose that decrease. Oh no, sorry, we don't need it to be out of the page. That's my bad. The change in flux should also be into the page because we want to, again, oppose that decrease. So if you want to oppose the decrease, you essentially have to reinforce that, the initial direction of the flux. So induced flux into the page. So using a right-hand grip rule, our fingers curl clockwise. So induced current is clockwise. So that's really good that we can determine that. All right, so looking over at this, we have a very similar sort of question. 35 seconds left, so let's boost through this. I'm getting an adrenaline rush right now. Interesting since I've already done this exam paper before, but hey. So our students push each side of the coil together, and now we have varying changes in magnetic flux, as we can see from the diagram. So we initially have an increase in magnetic flux into the page, then we have a decrease in magnetic flux into the page as before. All right, so we can see here that this is very similar to part B, so we can just flip around the directions of the current compared to from part B to part C, right? So if the current is clockwise before, it's going to be anti-clockwise now, and then it's going to go back to clockwise again as well. I'm obviously not expecting you guys to get this in this short period of time, but this is sort of like the mindset that you work through this. All right, so I'll just readjust my timer here. All right, so now let's start off with the short answer section. So the questions that I actually did work through. All right, so hopefully these questions are fresh in my mind, right? Since I've already used my reading time for them. So let's quickly blitz through this. Okay, so what do we have? We need to show that the velocity of the electron as these two fields are balanced is given by this equation. Well, let's quickly draw out our diagram. Right, so like I said, the electric force is pointing upwards and the magnetic force is pointing downwards. If you guys don't believe me, just use the right hand palm rule. Your thumb is to the left, not to the right, because we have an electron. It's negatively charged. Thumb is to the left. Well, we swap it around if you have a negative charge. All right, so we have that Fe, I'll use a different color, is equal to Fb, since our forces must balance out for our electron to move undeflected, right? And since our charges cancel out, we have that the speed is equal to the electric field strength over the magnetic field strength. All right, so let's move on. We have to calculate the magnitude of the velocity of an electron as it travels through the straight line by moving through path Y through the aperture to point Y with the electric field of this valley and the magnetic field strength of this valley. All right, so that's actually pretty nice because we just sub in the values. All right, so that's really good. The only trick about this question is the unit conversions. So just try to remember that. And doing this real quick. All right, so we end up with a speed of 2 million, which is pretty insane, but hey, this is an electron. Just to double check quick, is the speed greater than the speed of light? No, it's not, so still fairly reasonable. All right, at which points of X, Y, or Z could the electrons traveling faster than v naught arrive? So remember that v naught was the speed at which the electron is undeflected. So if the electron's speed is increased more than that, then would it travel upwards or would it travel downwards? All right, so let's have a think about this. When in doubt, write out as many equations you can think of, right? So let's just write out all the equations that are related to this scenario. This is the equation for the electric field, and we have the equation for the magnetic field. Now, which one of these two equations, if you think about it, would change depending on the speed? All right, so we know the forces influence which way our electron is deflected. If our electron is deflected upwards or downwards, in this case, the electron's magnetic force will increase if our speed is greater than v naught. Right, so if the electron speed is greater than v naught, then we have a downward deflection. All right, so we can see from this question that point Z would be the point of arrival for our electrons. So let's explain part CI. Okay, so why is the electron deflected downwards? Contrary to popular belief, you can actually write out your answers in dot points. So we'll just do that here. Alright, so the electron is deflected downwards towards Z because the magnetic force is increased, and that's the only force that is dependent on the speed. Right, so let's move on. Okay, so we also did this question in our reading time. So calculate the orbital radius of this satellite. So let's do that real quick. So we're given the radius of the Earth, and we're also given the altitude. So remember, guys, the altitude is the distance from the surface of the Earth, right? From the surface. That's a really important term. Alright, so this is a reasonable value since it's pretty close to the radius of the Earth. And again, nothing freakishly large. Alright, so part B. Now, this is the difficult one. Calculate the orbital radius. Sorry, not the orbital radius, the orbital period of the Icon satellite. Correct to 3 significant figures. Alright, so that is a really, really important detail, believe it or not, because you will get 1 mark for that. So 1 mark is going to be given just by writing your answer in the correct number of sig figs. So that is important. So this is actually really just a 3-mark question in terms of working out. We just get 1 free mark for our sig figs, and it should be a free mark if you guys have done enough practice for this. Okay, so like I said during my my reading time, or my reading time thoughts, you can say. This question is testing on the relationship between the gravitational field and the centripetal force. We basically always have to use this equation in any of these circular motion and gravitational field questions. That's basically a given. All right, so we asked to find the orbital period. Now, nothing in this equation tells you the period, but hopefully you guys remember that speed and period are related. So I can first of all try to find the speed, which is given by this, using some algebra. Then I can combine this with the definition for period. So period is equal to the circumference of the circle divided by the speed, distance divided by speed essentially. And so merging these equations together, we will get an equation that is entirely dependent on our radius, right? Since the other constants, since like the mass of the Earth and big G are always constant no matter what. So that's pretty cool if you think about it. It's only the radius that determines the period of our satellite. Right, so far we have gotten 2 marks from our working out, 3rd mark for subbing in our values and getting our answer. And then our final mark will be given by the correct number of sig figs. What was the value of big G again? Let me just open that up. It's been quite a while. Remember guys, all of these values are given in your cheat sheet, so there's no excuses for not remembering them because you don't need to remember them. Alright, so subbing all of our values into our calculator, we will get 0. Let me just see here. Oops, my bad. So we will not get 0. We will get 5,924 seconds. Is that right? All right, so like I said, we have got 5,923. I'm not sure why. I thought something went wrong with my calculator here. I'm using a CAD calculator, which isn't allowed, but that's all I got at the moment. All right, to explain how this satellite maintains a constant circular orbit without the use of propulsion engines. All right, so let's have a think about this. So I already formed 1 point in answering this question. So we have a gravitational force. Now, what else do we know about the gravitational force that is important for circular motion? All right, so let's have a think about this. The conditions for circular motion, one of them is the fact that we need a centripetal force. But hopefully you guys remember that just because you have a center-seeking force doesn't mean that you're going to have a constant clean circular orbit. Because you could have a center-seeking force, and if that force varies in magnitude, well, then you could have something like an elliptical orbit, right? If let's say the force is really large at some angles and really small at other angles, then our object will deflect by a different amount at different instances, and so that is something we need to keep in mind. So those are our two conditions. They will give us our 2 marks as we've determined during our reading time. So one point being the fact that the force has a constant magnitude. Right. Should say the gravitational force. And the second dot point being that the gravitational force is a center-seeking force. Right, since it points to the center of the Earth at all times. All right, so those will be enough details for you guys to get the full marks. Now you don't need to fully explain the context of the question, especially for these small 2 mark responses. All right, moving on. Analyze the graph, and we've already gone through this in our reading time, so we don't need to reread this question in too much depth. So find the area of this graph. So this shaded region. So let's have a look at this. This is a gravitational field strength graph. What is another trick we can spot? Well, the units are in kilometers. So those are the 2 things. If you guys don't have this general formula in your cheat sheet, or you're not familiar with this, make sure to note this down. So this is the formula for the change in GPE. All right, so always write out your formula first when you are doing these responses. You'll get 1 mark for just writing out your formula and subbing in the values into the formula. So I know that's pretty crazy, but that's how it works. Sometimes you just get a mark for just the formula itself, which is pretty crazy if you think about it. All right, so we have a graph that models the gravitational field, field strength, and the distance from the center. Now, the formula that I've laid out has a limitation. It's an approximation, right? You have to approximate the area. Now, do I need to approximate the area for this particular graph? So if we think about it, I have written down the formula, but do I need to count the number of individual squares to approximate the area? So do I need to go 1, 2, 3, 4, 5, 6, 7? I probably don't, because we have a shape that we are hopefully familiar with, right? It's like sort of like a triangle. You sort of this triangle here, and you can find the area of that triangle. You actually have a trapezium, right? That's not an obvious connection, and you can just use the formula that I've given down, which normally applies for your curves, but you can still use this for a trapezium as well. It just won't be the exact value. Here, on the other hand, we can actually find the exact answer. All right, so we can do that over here. If I just erase that, we have to find the area of the trapezium. You can also break it down into 2 shapes, so a triangle and a rectangle, but that is up to you. All right. All right, so this is the formula for the trapezium. Let's sub in our values. So half of A plus B, which is the average, essentially, of the two heights of the trapezium. But you obviously don't need to know that for physics. All right, so subbing in these values into our calculator, we get 5.4 times 10 to the power of 6. Now, what are the units? Well, the units are joules per kilogram. Since the area does not just give you the energy, it's the energy per mass of object that we have. All right, so we need to multiply this area by our mass to actually get the change in the gravitational potential energy. Now the mass is given in the question. It is 288 kilograms. All right, so multiplying that value, we get 1.56 times 10 to the power of 9 joules. All right, so we skipped over this question because just judging by the diagram, it was relatively straightforward, or I should say familiar. So we went over this during our reading time. So let's just refresh our minds. What was this question about? It was about EMFs and Lenz's law. Right. So what was the first change in flux? We had a decrease in the magnetic flux going into the page. Looking over this. By the way, guys, don't worry if you feel like you can't just remember these questions in that short amount of time like I've done, because I've already done these questions so many times before. But I'm just sort of pretending like I haven't seen them earlier. So guys, you can just play along. All right, so what do we have? We have a decrease in flux into the page, and that is what the first question is actually asking us. So the magnetic flux decreases. Now explain using physics principles why this ammeter registers a current in the coil, and explain the direction of the induced current. All right. Again, guys, you can write in dot points. I would suggest that your dot points be almost like full sentences, and there should be like some connection between the dot points. Dot points are just like a formatting thing. Just because you write in dot points doesn't mean you should write in really nice small phrases or something like that. It should still be sentences that are all connected with each other. So that's how you can actually get an answer that flows from one to the other part. So why does the ammeter register a current, and what is the current itself? All right, so the first part of the question can be answered using Faraday's law. So that is the first part of the question. That should give you 1, maybe even 2 marks just from that. I would say approximately 1 mark. Now we have to incorporate Lenz's law that will tell us, the direction of the current itself. Now, of course, you don't need to write in this much detail, but just to be safe, I always like to include a brief description of the laws that I'm using or the theorems that are applicable to some question. So that's why the first 2 dot points is basically just a word salad about Faraday's and Lenz's law. You obviously don't need to write that much, but that that is just for, just to be safe that you actually get the marks. All right, so part C. Very similar question, as we can see just from a quick glimpse of the diagram. So the students push each side of the coil together, as shown in figure A, and the coil returns to the original shape temporarily, and then changes to the shape shown in figure C. Essentially, the students now start to squeeze the coil inward instead of stretching it out. So before they were stretching the coil outward, now they're squeezing the coil inward. So what is the result of this? Well, we're going to have different changes in magnetic flux. Hopefully you can see that from the diagram. Before we had a decrease in the magnetic flux into the page. Now we have an increase of magnetic flux into the page. Right? Because as the area of the coil has increased. Right, you can see we have 2 x's. We have 2 magnetic field lines passing in figure 6a, and then we have 6 magnetic field lines passing in figure 6b. So that is basically a tripling of the magnetic flux, just from the diagram. However, in figure 6c, the area now decreases again. So now there's less area, there's less scope for the magnetic field lines to actually pass through. So now the flux has decreased back again. So we have an increase, then we have a decrease again. All right, so because of this increase decrease, you should be able to judge without using the without using Lenz's law over and over again, that the induced current will change, right? It will flip direction from one transition to the other. So before, our induced current might be anti-clockwise, and then it's going to go into clockwise from figure 6b to 6c. And so that's essentially what this question is testing on, the idea that current is dependent on change in flux. All right, so I know this is a behemoth of a response, but believe it or not, you do need to write this much to get, or to at least be confident that you get those 2 marks. The first part of the response is explaining the transition from 6a to 6b, how we have an induced flux of or pointing out of the page. So an induced current is anti-clockwise in here, and then the induced current starts to flow in a clockwise direction due to that change in the magnetic flux, if you guys understand what I'm trying to say. So before it was an increase in flux, now it's a decrease in the flux. So the current swaps around, and hence we do have this almost like this alternating current that's flowing through. All right, so that is it. We've done the hardest questions, at least the ones that we could identify straight off the bat. Of course, there are going to be harder questions that are still left to go, no doubt about that. But we still gave these ones a go, so that was good. All right, so let's start from question 1 in the MCQ section. Looking at the time, we have only spent around 35 minutes so far, which isn't too bad. All right, so I will quickly go over these questions, and then we'll meet up in 5 or 10 minutes. Alright guys, so that was quite a run. Now we will move on to the short answer section. Alright, so we got the MCQ out of the way, so don't need to have that in the back of our minds, especially when we're under exam pressure. I know how that can feel when you have like 20 questions left to go and there's only 30 minutes left. So that's why we got that over and done with. Definitely don't want to leave that till the end. Okay, so question 1. We have two bar magnets that are close to each other. Well, that's pretty obvious from the diagram. Show the magnetic field lines between these two magnetic poles. Our north and south poles are at. So we have unlike poles. That means we're going to have attraction. So poles, remember guys, work in a very similar fashion to our charges. Right? So magnetic poles, like repels, unlike attracts, right? As we can see here. On the outer edges, we're going to have curved magnetic field lines, which is where the uniformity of this magnetic field starts to break down. But inside, in the middle region, we're going to have straight magnetic field lines because the magnetic field is relatively uniform. All right, so describe the three gravitational, magnetic, and electric fields. All right, so we can see that from the table. According to understanding of the physics and current experimental evidence, these three field types can be associated with only monopoles, only dipoles, and both monopoles and dipoles. So we have to complete this diagram, explain, or not explain, but indicate whether each field type is associated with only monopoles, only dipoles, or both monopoles and dipoles. Gravitational fields, well, we know gravitational fields are only attractive. We have one type of pole, which is the mass, essentially. That is our pole. Magnetic fields, well, magnetic fields are interesting because have you ever all seen a North Pole magnet by itself or a South Pole bar? No, you haven't, right? So we have magnetic dipoles. They exist together. Electric fields, on the other hand, can exist as both monopoles and dipoles. So you can have individual electrons, protons separate, but it can also have you can also have the collection of charges together. So for example, you can have a molecule with protons on one end and electrons on the other end, so that is a dipole, but for electric fields. All right, so moving on, we've done questions 2, 3, and 4 already. Question 5. So we have a DC generator. We already determined that from our reading time. The area is given by this, so that's important. We have a uniform magnetic field. The loop is rotated with this particular frequency, and it's rotated in this clockwise direction, as you can see. The ends of the loop are connected to a commutator, so that should definitely ring some bells. We have a DC output. In which direction, clockwise or anti-clockwise, will the induced current travel through the loop for the first quarter turn as shown? All right, so for our first quarter turn, till that loop is in this vertical position, right? So going from the horizontal to the vertical position. All right, so let's have a look at this. So which way is the induced flux? This is an induced flux question. It's based on Lenz's law, of course. So we are going to have an increasing magnetic flux to the left. So the magnetic flux increases to the left, since now there's going to be increased area for these magnetic field lines to pass through. So that means our induced flux should try to prevent that increase by pointing to the right. So using our right-hand group rule, our induced current should essentially flow in this anti-clockwise direction, though it depends on which way you look at it though. So it does say it's as seen from above. All right, so I didn't notice that earlier. But this is where the current is flowing. Right, so that is based on our right hand group rule. All right, so as viewed from above, we should try to determine how is that, whether that current is clockwise or anti-clockwise. So we have to pick one direction. I know perspective can be really confusing, especially for these questions. We have to really try to hone in our spatial reasoning. So try to imagine you view this circuit from above. How will it look like? So it will be anti-clockwise. Same way if you look at it from the right as well. Yes, so it will be anti-clockwise. All right, so let's now move on. All right, so determine the average EMF measured in the loop for the first quarter term. We will have an EMF. So this key term should remind you of Lenz's law. That's why everything in this question is based on Lenz's law. EMF, Lenz's law, those two keywords go together. The formula for EMF is that is equal to the integer multiple of the change in the magnetic flux, the rate of change in magnetic flux. Sorry, I shouldn't say, oh, sorry, actually it is the integer multiple. I just realized that it is the integer multiple, since you can't have like half number of coils or what. Anyways, never mind. So this is the EMF formula. The hardest part about this question is determining how our magnetic flux changes, right? So do we have a change in area, or do we have a change in the magnetic field strength? We could actually have both, but that would be, well, above the scope of this unit. We have a change in the area available for these magnetic field lines to pass through. So hence, we can rewrite the formula for the magnetic flux into something like this. Now, don't worry if you guys haven't seen this before, but this just makes it just helps with my understanding. If it doesn't with yours, then that's completely fine. Now we can sub in our values here. So the number of coils of wire, that is, what is that? Well, we can just assume that that is 1 in this case, since the number of coils have not been specified. We do know, however, the magnetic field strength, which is again a very important detail. The change in the area, so this is another tricky part. We'll be going from a 0 area available for the magnetic field lines to a complete area of the coil. We're going from horizontal to vertical. So let's write this out. So these are the dimensions. That is the final area subtracted by the initial area. Now the change in the time, well, that is another important detail. So I'll just make a break here and we'll determine that. So the frequency gives us something about the period. The period is 1 over the 50 Hertz frequency. Guys, just pause the video if you can't follow me in this pace, right? You guys can just pause the video and take it through in your own time. I've done a lot of these questions before, so I definitely have a lot of practice. But don't stress if you guys can't follow through this as I'm going through. But this is the change in the time. It is 1 over 200. Since that represents the time taken for a quarter turn, right? So that's why we'd have to divide that period by 4. So divide that 1 over 50 by 4 and you get the change in time. And so subtracting and dividing all of these values together and multiplying, we will get the voltage that's induced to be 7 times 10 to the power minus 5 volts. All right, don't know why I wrote that in such a massive font, but there we have it. Okay, so on the axis below, we have to sketch the output voltage versus the time. I'm already betting a lot of people got this question wrong because, what do we have? We have a DC generator, and for DC generators, your voltage is always positive. It's always as a constant direction. And yeah, definitely a lot of people would have gotten this question wrong. It's a DC motor, right? Oh, sorry, not a motor, a DC generator. So 3 things are important for these EMF graphs. 1 is the period. 2nd is the amplitude. And 3rd is the overall shape. We've already talked about the overall shape. We need our voltage to have a constant value, a constant sign, I should say, so it's positive or negative all throughout. I also should have an amplitude and a period. So the period, well, we know that is 1 divided by 50. Right, so this is the period. Since we knew from the question that 50 hertz was the frequency, so 0.02 is the period. That will give you 1 rotation. What is the amplitude? Well, the amplitude relates to the maximum EMF that it can generate. In this case, well, let's have a think about this. Can I determine my maximum EMF? So a lot of people, they would have written this value down as their amplitude. The problem is that's the average EMF. That's not the maximum EMF. So if this was a magnetic flux graph, then you could determine the maximum Y value. In this case, you can't, so we can ignore the amplitude, but we covered the period already. All right, so our graph should look like this. It should be a sinusoidal wave. And if any of you guys do specialist maths, you should realize that this is basically just the absolute value of your normal sine graph, or cosine graph, whichever way you want to call it. Now, let's have so this is the overall shape of the graph. Let's have a think about this. So I just noticed that I might have made a mistake with my answer, because my initial value for the EMF, I've said that 0, but is the initial value of the EMF 0? Remember that EMF relates to the change in flux. Right. If there is no change in flux, or a momentary 0 change in flux, then you have a 0 EMF. The problem is the coil is starting at a horizontal position. That's actually where you have a maximum change in flux, because that's where you're going from a decreasing flux to an increasing flux. Your literal direction in the flux swaps around at the horizontal position. So if you assume that the coil is rotating all around, then the change in flux is actually at a maximum value at the horizontal position. So we actually start our graph up over here, right? Not down over here, since our coil starts at a horizontal position. And so that is a really important detail. At the horizontal position, you have a maximum change in flux, hence a maximum EMF. I should say maximum rate of change in flux, so my bad. And there we have it. So this is our rough sketch of this EMF graph. All right, that will do. Now, part D, we have to suggest 2 modifications that could be made to our apparatus as shown in figure 4, that will increase the output EMF of the DC generator. Okay, so we have a DC generator. How can I increase the EMF that comes out of this? Remember that EMF relates to the change in flux. Now there's one thing I can do, which should be fairly intuitive. I can increase the value of N, and that will increase the value of the EMF. Increase one variable and the other variable also increases, so I can increase the number of coils. What I can also increase, however, is the frequency, because that will let me decrease the time that it takes for the coil to rotate. So if the time decreases, aka the frequency increases, then the output EMF will also increase. So those are my two things. All right, luckily we've already done question 6, so that should definitely give us confidence when we are progressing through this exam. And moving on, we have another Lenz's law electromagnetism related question, this time to do with transformers. All right, so this is an interesting diagram. I actually don't remember this to be honest, so hopefully I don't make any mistakes, but yeah. So rechargeable electric toothbrush uses a transformer circuit as shown in figure 7. Remember that with transformers, we have two coils. We have the primary coil and we have the secondary coil. The primary coil has the role of receiving the input current, and the secondary coil has the role of receiving the current from the primary coil. So a transformer is basically a way for you to teleport the electricity from one coil to another through thin air, essentially, using the principles of electromagnetic induction, right? Faraday's law, Lenz's law. Now, enough of the theory, let's actually analyze the question. So the secondary coil inside the toothbrush is connected via an iron core to the primary coil, as you can see, which is connected to the main power supply. That was exactly what I was talking about. The power supply has this RMS voltage, and the toothbrush requires this 12 RMS voltage. The average power delivered by the transformer is 0.9 watts. We can assume the transformer is ideal, i.e. no power is lost. All right. Part A, calculate the peak voltage in the secondary coil. Well, using the definition of RMS voltage, we can rearrange this formula, right, and find that the peak voltage is nothing more than the square root of 2 factor over the RMS voltage. That was a weird way of saying it. Essentially square root 2 times 12. Okay, and that would be around 24, around double. Also not double, around 18, I should say, around 1.5 of our actual value here. So plugging this into my calculator, this is what I get. 17 volts. Now we have to determine the ratio of turns between our primary and our secondary coils. So the coils in the primary, NP, divided by the coils in the secondary, NS. What is that equal to? Well, that is equal to the voltage, in the primary over the voltage in the secondary. Dividing these two values gives us 20, so that is our ratio. You can also write this as 20 to 1, but it doesn't really matter. Part C. Calculate the RMS current in the primary coil while the toothbrush is charging. Alright, so let's work through this. We know that we have an ideal transformer, hence our ratio equations do apply. We don't have any power loss through our primary to the secondary coil. Our electromagnetic induction is perfect. That's essentially what we can assume. Now we're trying to find the current in the primary coil. So what do we know? We know the power. Power relates to current, right? So we know the power in the secondary coil, which relates to current, right? The power in the secondary is the exact same as the power in the primary coil, by the way. And we also know the voltage in the primary, so that's something we can use. Alright, finally, so now we have a mechanics question. Hopefully, just by judging from the diagram, we can see that this is a horizontal circular motions question. So we're given a small ball of 1.8 kilograms rotating in a horizontal circular path at a constant speed, so that's uniform circular motion, suspended from a ceiling by a 0.75 meter long string. Now, from part A, we have to label the two physical forces that are acting on the ball. One of them will always have to be the gravitational force. The other force is the force of the string, which is a tension force. Now, part B, we have to calculate the speed of the ball. So how would I approach this question? Well, in an actual exam scenario, I would analyze my force diagram, and I would try to find something from the forces that connects with this situation at hand. In this case, we have circular motion. You need a centripetal force for circular motion. So why don't we use that connection to our advantage? So we need a centripetal force. We know the formula for the centripetal force, right? We know that the centripetal force is equal to mv squared of r. Now, there we go. That's our connection. Centripetal force relates to the speed of the ball. Centripetal force is the force that also relates to our force diagram. Hopefully, you guys can see how I'm using that connection to my advantage. How can I write this centripetal force in terms of the forces that I have? Well, I need the tension force. Right? The horizontal component of the tension force is the centripetal force. Alright, so I will redraw this force diagram, just a rough sketch down over here. Alright. So there are two components to the tension force, the vertical and the horizontal. Now, the vertical part of the tension force, which is T cosine 25 degrees, that must balance out with the gravitational force. Otherwise, my ball would be floating up in the air. It would just be moving up and down. It is floating up in the air in this case, but if there was a net force, vertically, then the ball will be pushed up or down. In this case, it's not. So what I can do to find the tension force is I can equate these two expressions. Right. Now, plugging in the values for my mass and 9.8 and cosine 25 degrees into my calculator, I will get the value of the tension force. Alright, so summing up everything, what I've done is I have used my centripetal force, equated that with the horizontal component of the tension force, right? Because that is the part of the tension force that's pulling the ball inward and causing it to rotate in this circular fashion. Using a whole bunch of algebra and substitutions, I've got my value for the speed of the ball. Alright, so moving on, we have another ball question, this time with ideal springs. So an ideal spring compressed by 0.15 meters is launched in the horizontal direction. We know the mass of the ball is 0.2 kilograms. That's placed in contact with the compressed spring. The spring is released and the ball is propelled, of course. Then the ball will fall down eventually. So what can we tell from the scenario, from the diagram? We know that this question is a springs question, so we're going to have some like energy, some Hooke's law incorporated into this. This is also a projectile motions question because we have this massive gap, this massive open space here. So of course that probably means something, and so the ball will fall down. And yeah, that is related to part BA, as we can see here. Find the speed of the ball after it has fallen a vertical distance. Part A show that the magnitude of the initial speed is 12 meters per second. So how can we do this question? Well, always we have to try to find connections, right, between what we know and what we're trying to find. In this case, we're trying to find the initial velocity. But what do we know about the scenario? Well, we know for a fact that the spring is compressed by this much distance and that the mass of the ball is 0.2 kilograms. And we also know the spring constant. So let's try to sort of like relate that to the initial speed of the ball. All right, let's try to relate those values to the speed of the ball as it is launched. We're going to have to use energies in here because we can't possibly solve this with kinematics. That will be way too complicated, wouldn't it? So we have spring potential energy out here when the spring was compressed, and then we have kinetic energy out out over there. Spring potential energy converts into kinetic energy. It's that energy that is responsible for propelling the ball. Now we can use the values that I've talked about earlier to complete the left-hand side of the equation, right? Because we know the spring constant and we know the compression of the spring. We also know the mass of the ball, right? And so that will let me find V. Right? I only have one unknown in this equation, and that unknown can be isolated, and so then I can find the initial speed, which is sort of like the final speed in this energy equation, but it's the initial speed in that overall projectile motion scenario. Alright, so moving on, we have to find the speed of the ball after it has fallen a vertical distance of 2.5 meters, projectile motion. Alright, so this ball has traveled in this parabolic path. It strikes the ground with a particular speed. The problem is we can't, or well, we can, but it's very hard to find that final speed with just kinematics. We could find that final speed with just kinematics, but that will involve projectile motion. If you guys remember, with projectile motion, you have to split your forces into, or split your motion, I should say, into two parts, x and y dimensions. You can solve the motion in the vertical plane first, and then in the horizontal plane try to equate the time in those two dimensions and all of that jazz, but that will be really complicated. It will take a long time. So what is my favorite approach for this question? Since we have to find the overall speed that the ball strikes with the ground, not just the final vertical speed or the final horizontal speed, I would just stick with conservation of energy, right? Guys, conservation of energy is a hack, right? It's not something to feel worried about. That's meant to save your life, really. It's such a good shortcut. So we know that initially we have gravitational potential energy and we have a small amount of kinetic energy. After the ball has fallen, right, just before it lands to the ground, we have a massive amount of kinetic energy. So all of that GPE essentially converts entirely into kinetic energy. Right. Now you guys might wonder why I didn't use GPE for part A. Well, that's because there was no change in height in part A, but in part B there is a change in height. Alright, so subbing all of these numbers into our equation, we end up with the final speed being 14.2 meters per second. So question 10. Just from the diagram, we can see this is a collision scenario. Mentally, in your mind, try to relate collision with conservation of momentum. Right. Hopefully with the practice exams that you guys are doing, you are starting to find these trends in these questions. So, you know, we've already seen a lot of questions involving a ball moving in a horizontal circular motion. You've obviously seen a lot of questions with carts and vans that are colliding with each other, and they just draw them as rectangles, and it's conservation of momentum. So a lot of these questions repeat over and over again in VCAA physics. So that's why I know what principle to apply without even reading one word of that question stem. So what do we have? We have a person who's designing a computer simulation program, where we are simulating a car of mass 1200 kilograms moving at 10 meters per second that collides into a stationary van. You can see that from the diagram, so that's not too important to read. The van then moves off at 6.5 meters per second. Calculate the speed of the car after the collision. Right, the speed of the car after collision, and indicate the direction that it would be traveling, and we have to show our working. So from the conservation of momentum, we can list out this equation. Alright, so we've both given the magnitude of our velocity vector of our car and the direction as well, which is to the left, since negative signs generally mean to the left. Alright, now explain using appropriate physics why this collision represents either an elastic or an inelastic collision. Remember that these terms are to do with the conservation of kinetic energy. Right, so the question is kinetic energy conserved? Right. So you guys have to remember that kinetic energy conservation, it's more of like a privileged condition. Right? You're not always going to have kinetic energy being conserved. It would be great if that was the case. Right? Save a lot of fuel, but we don't always have that. So let's see if kinetic energy is conserved. So what we have to do is we have to first find out the total kinetic energy of the system initially, and then we have to find out the total kinetic energy of the system after the collision. Alright, so judging from our answer, since the kinetic energy initial is not the same as the final kinetic energy, we can say that some energy has been lost throughout the collision. And so therefore, this is an inelastic collision. Just remember, guys, that if for some reason the final kinetic energy in your calculation is more than the initial kinetic energy, you've made some mistake, and so it's best to go back to your working out. Right, that doesn't make any sense. You're not going to randomly add in new energy into the system. So if that happens, just double check your answer, and then you know you made a mistake. All right, so from this we can get our final mark by saying that there has been an inelastic collision. All right, so now we are incorporating the idea of time into this. So the collision between the car and the van takes 40 milliseconds. Time plus momentum. What does that remind you of? Well, open up your formula sheets. We bring up this formula. The change in the momentum is equal to force times the change in time. All right, so that's the formula that should first pop up in your mind when you see time and momentum included in the same question. All right, so we have to determine the magnitude and the direction of the average force by the van, right? Oh, sorry, on the van, I should say, by the car. So the force that the van exerts on the car, right, which is to the right. Of course, we know that because the car is moving to the right. So that's the direction. But what is the magnitude? All right, so let's have a look at this. So we need to find, first of all, the change in momentum of our car. Right, oh sorry, not of our car, of our van. It doesn't really matter though if you think about it, because the impulse of the van and the car is going to be the same. It's just going to be in different directions because of the conservation of momentum. All right, so the force exerted on our van is 357.5 kilonewton. By the way, the reason I quickly realized that I made a mistake was the fact that the kinetic energy and the momentum of the van is 0 initially, so it doesn't make any sense for me to get a value for the momentum of the van initially. That's why I knew I made a mistake. But now let's move on to part II. We have to calculate the magnitude and the direction of the average force on the car by the van. Two ways to do this. One, you can either be a Dumbo and go through this entire process again with the van and the car again, or you can be a little bit more smart and you can just use Newton's third law, right? And that's what we're going to do here. So we know the impulse is the same on the van as it's on the car. The forces are going to be the same as well. All right, so we have a force on the car being 357.5 kilonewtons to the left this time because of that negative sign. And this expression is just Newton's third law. Hopefully guys recognize that. All right, so let's move on to question 11. 56 minutes, so time is running out, but let's just smash the last couple questions out. All right, so this is the special relativity question. You'll always get a special relativity question in your exam, so that's why this is the special relativity question, because you're always going to get that. So you can expect that to happen. So an astronaut that has left the Earth traveling on a spaceship at this much speed towards the star known as Sirius, which is located 8.61 light years away from the Earth. This is a unit for distance, by the way, not time, just because it says years, it's a unit for distance, as measured by the observers on the Earth. So that 8.61 light years is a distance measured by the observers on the Earth. That's really, really important, because everything with special relativity is based on the idea that perspective matters. How long will the trip take according to the clock that the astronaut is carrying on his spaceship? Okay, so let's have a think about this. Is this proper time or dilated time? That's the first question that we have. This will be proper time because the astronaut is himself stationary in his own spaceship. So he's going to be measuring proper time. That's what it's sort of called proper, because that's from his own more authentic perspective. Though that's a bit, I don't really like the wording, but that's how you can think about it. Okay, so we need to find proper time. So how will we do this? Well, we know the speed at which the astronaut is traveling, and we also know the distance that he is traveling. All of that's from the observers on the Earth. Now, there's two ways you can do this. One way would be to use special relativity. You use the time dilation formula. And Another way to do this would be to first of all use your kinematics approach, right? So we know the distance, we also know the speed, so how can we find the time from that? Well, we can first of all find the dialectic time, right, from our speed and our distance. So the dialectic time is equal to 8.61 light years divided by 0.800 c. Now, the speed of light and the light in the units in the numerator, they cancel out. And so what we're left off with is 10.76 years. That is our dialectic time, right? Now, why is this dialectic time? Well, that's because the observers on the Earth, they're measuring dialectic time. Yeah, because for them, the spaceship is moving from one position to another position. So that position is changing, and hence that is dialectic time. So excuse what I said earlier, you do need to use special relativity. You do need to use this equation. We can rearrange this to find the proper time, which is what we are looking for. Substituting the value for the Lorentz constant, we get 6.44 years as our answer. Right, so I've already done that on my calculator. Part B. Is the trip time measured by the astronaut in part A proper time or dialectic time? All right, and it is, of course, proper time. We can explain that as so. All right, so moving on. Here we have a Young's double-slit experiment question, as we can see from the diagram. We have a laser light that comes through two slits, S1 and S2, that are this distance apart. The rays from the slit meet on a screen 2 meters from the slits to produce an interference pattern. Point C is the center of the pattern, as you can see here. What is the question asking us? So there is a bright fringe at point P, as we can see from this small figure underneath. Explain how this bright fringe is formed. So this is a worded question, so we can quickly go through this. Right, so the explanation for part A was very similar to the typical explanation we give for interference, but to just explain the path difference formula, you can just write out the formula. You don't need to write it out in this using this much words, so no need to write out into your multiple wavelength. Just n times lambda is enough. The key word here is in phase, so try to use that in explanations, and so that will give you the 2 marks. Part B, on the other hand, is more so a numerical question. So using the fact that the distance from the central fringe to point P is this much, we have to calculate the wavelength of our laser light. So what do we know? Let's use the general principle of going from known to unknown. So we know that the distance from C to P is this much. Now, what's the formula that reminds you of distances between fringes? Well, it should be, hopefully, the delta x formula. So let's try to relate this distance to delta x. So how many fringe spacings can we fit in this distance? Well, we have 1, 2, 3 fringe spacings from the looks of it. No, actually we have 4. So if you divide this value by 4, the 1.26 centimeters, you will get delta x. You might not have realized that just by looking at the diagram, but that is actually how you will do it. Right, so we have 4 fringe spacings. Alright, so moving on, straight off the bat, we have a standing waves question here. Anytime you hear the phrase guitar string, you know it's going to be a standing waves question. Whenever you see a standing waves question, try to pinpoint the medium boundaries. So what are the medium boundaries that are surrounding our particular medium, right? In this case, the string. We have fixed ends or free ends, yeah? So in this case, we have 2 fixed ends, and that's going to determine the formula that you're going to use. The reason I could easily pinpoint that was from the fact that we have nodes at these points, right? If you have a fixed end, your string can't move up or down at those points. So it's fixed, it's clamped into that point, and so that's why it's a fixed end. So our string is 0.8 meters long. It is vibrating at 250 hertz. A standing wave is created. We have to calculate the speed of the wave in the guitar string. So we know the length of the medium, that's fixed. Right, that's one known value. And we also know the frequency that is associated with this particular harmonic, which is the fundamental frequency. Alright, so hopefully you guys remember that the wavelength that can fit inside our medium for a standing wave is equal to 2L over N for this 2 fixed end condition. We know that n is equal to 1 since this is the first harmonic. Well, this is like the smallest, or I shouldn't say the smallest wave. This is the largest wavelength that we have. Right, largest wave, or the smallest frequency. Alright, so this is how I solve this problem. Again, you use the principle of known to unknown. I know 3 facts about this. I know the fact that we have a medium length of 0.8 meters. I know the structure of my standing wave. We have a first harmonic. This is where we have the largest wavelength, largest wavelength, smallest frequency. We have 2 fixed ends surrounding our wave, and we also have a 250 hertz frequency. Using these 3 known values, you can solve for the speed of the wave. Now the frequency of the guitar string has been tripled to 750 hertz. We have to sketch the diagram for the wave. Now, how did I come across this? Well, the frequency has tripled, so that means that this is the 3rd harmonic. Remember that we can only increase our standing wave size by integer multiples. So you can have like first harmonic, second harmonic, third harmonic. This is the 3rd harmonic. Right? There's only one other harmonic between the first one that we covered and this one. Right? The number of harmonics corresponds to the number of half wavelengths that we have. So that means I have 3 semicircles, almost in a sense, inside my standing wave. So moving on. This is an interesting question. We are looking at an electromagnetic wave. So figure 13 shows the representation of an electromagnetic wave. Correctly label figure 13 using the symbols electric field, magnetic field, speed of light, wavelength. Okay, so electromagnetic waves, aka light waves, are made up of an electric field and a magnetic field that oscillates about, right? And they're perpendicular to each other. This is also something that supports the fact that light is a transverse wave, so you guys might want to note that down in a cheat sheet. Right, because electric fields and magnetic fields, when they're changing, right, repeatedly, they're almost like transverse waves themselves. All right, so now we have the signature photoelectric effect question, which again, you can always have these types of questions there. So special relativity, photoelectric effect, Lenz law, always going to be in your exam. All right, so typical photoelectric cell setup. Don't need to read that. We have the photocurrent versus voltage graph as shown here. So we're changing the voltages, the stopping voltages, and also the forward voltage as well. And we're measuring the effect on the current. We have to draw another graph resulting from another experiment for light with the same frequency but triple the intensity. Intensity relates to the current, but if it's the same frequency, that means the energy is the same. So the stopping voltage is the same, but for a tripled intensity, our maximum height of our graph, you can say, is tripled. All right, so why does the photocurrent become zero at the stopping voltage? Well, you just copy paste the definition of the stopping voltage there. Now, question 6. Oh, so that was a pretty short question. So lucky for us. All right, so looking at this diagram, we can sort of see a diffraction pattern, and we have electrons. Electrons and diffraction usually don't go together, except for one topic. That topic is, of course, our wave-particle duality. Right? Particles and waves are more similar than we initially thought. Alright, so calculate the kinetic energy of the electrons that are fired through a crystal, producing this diffraction pattern. Right, as shown in this figure. We know the mass of this electron, so let's calculate this. The kinetic energy of anything really can be described in terms of its momentum as well. This formula isn't too helpful for this case, but I just thought I'd bring this up here in case it might be useful for some of you guys later on. You might get a question where you know the momentum and you want to quickly find the kinetic energy from that. You can use that as well. In this case, it's just a matter of subbing in our speed and our mass. Alright, so now this electron has been replaced by an X-ray beam, and what do you expect? The diffraction patterns have the same spacing. In this case, we have a lot of topics that are combined in this one question. Diffraction, kinetic energy, wave-particle duality, all in one. If the spacing in the diffraction pattern is the same between this X-ray beam and the electrons that are fired, that means that the ratio of the wavelength and the width of the slit must be the same. Right, now, we can assume that W is the same, right, for both the X-ray and the electron. So that means that the wavelength for the X-ray is the exact same as the wavelength for the electron. Now, I'll know the wavelength of the electron because that is just h over p. Right, and we can quite easily determine that just from the information we're given up here. Right, so using the same procedure as I've talked about earlier, going from known to unknown. So we know the connection between the X-rays and the electrons. Their wavelengths are the exact same. I know the wavelength of the X-ray now, and if I know the wavelength, I also know the energy. Right, so that's how we can work through this. All right, so moving on, question 17. And my voice is getting really, really dry, so hopefully we can get through this soon enough. So we have an emission spectrum of helium gas. The spectral lines are shown here, indicate the spectral line for the photon with the lowest energy. So the energy of a photon is given by hc over lambda. So if the wavelength is big, then the energy is small. So what is the largest wavelength that we can spot here? That is 668 nanometers. Moving on to part B, calculate the frequency for a given wavelength. Well, that is not too difficult, is it, right? If you know the wavelength, you know the frequency as well, given you know the speed as well. All right, so moving on, finally a worded question that we can actually have some discussion about. So explain why only certain wavelengths and therefore only certain energies are present in the helium spectrum. So this is also using the idea of wave-particle duality in a sense. You obviously don't need to go in that much depth. You can talk about how we have certain energy levels in our atoms, and so therefore only particular changes in energy can happen. Our atoms can only absorb particular energies for light, hence particular wavelengths of light. All right, so finally, question 18 is the final big question. 27 minutes to go, so we can quite easily smash this one out. So we have an electrical circuit with a 24 volts power supply, luckily it's DC. There's nothing too complicated there. We have students modeling the effect of resistance of these electric cables on the transmission of electric power. I wonder why I actually didn't go over this exam before. I actually did not do this for VC. Luckily, still made it past. Anyways, they model the cables using circuits shown in Figure 18. We have electric cables, and we have that connecting to a light globe of a constant resistance. Alright, so assuming a 24 volts power supply, describe the effect of increasing the resistance of the electric cables on the brightness of the constant resistance globe. Alright, so we just use some electrical principles there, and yeah. Alright, so moving on, we actually are given some data for this experiment. So by the looks of it, we are changing the resistance of the cables to measure the current in the cables. Right, so part A, identify the independent and dependent variables. So the independent variable is the variable that we change, so that will be the resistance in the cables. By the same token, the dependent variable is the variable that we are measuring, is dependent on another variable. So that will be the current in the cables which we are measuring. Right, just because I have OCD, I'll also write out the units as well. So those are our two variables. Now, almost missed this. We also have to give the reasoning. So just talking about what I said. All right, so the independent variable is the variable that is altered, so it is the resistance. The dependent variable is the one that is measured. You can also write that down here. I didn't realize we also have to give the reasoning, so that's why I probably would have spaced my response much better if I was doing it in the actual exam. But for here, we'll just leave it that as it is. I probably still will get 2 marks, to be honest. Hey, at least I talked about the independent variable. All right, so do I have to fill in the table? Oh, that's part D. Okay. So to analyze the data, the students use the following equation to calculate the resistance of the cables in the circuit. Show that this equation is true for the circuit as shown in Figure 18. So we have a connection between the resistance in the cables that we are changing and the current as well, and the current in the cables. So how can we try to find a connection between them? Well, we can use total voltage, right? The total voltage in a circuit is conserved. That comes from energy conservation. And we can complete this equation to sort of find a connection between the current and the resistance. So I'll complete this out and then we'll meet up. Alright, so now we have to plot the linearized fit between our resistance values and the reciprocal of current on the x-axis. Right, so even though we are changing the current, let me alright, so that's interesting. So we're changing the current. No, so we're changing the resistance and we're measuring the current. Even though the so the axes are the other way around, but hey, that's all right. That's just because of the linear fit, I suppose. So that's just to make it easier. Technically, the independent variable should be over here, right? And so the 1/I should be up there, but that doesn't matter. You can't judge the VCAA loads, can you? Yeah. It is what it is. All right, so let's plot this data, and so we can all go home. So that is all done. Of course, you guys will be using a ruler to sketch your line of best fit, but this is the best I can do on my tablet. So I've drawn my uncertainty bars, which are the horizontal uncertainty bars, since it literally says it's in the x direction. We don't need to do the y direction uncertainty bars, so that's good. And don't worry too much about the exact scale of the uncertainty bars. As long as you're around in the ballpark and you don't need to have exact precision in terms of the length, but as long as it's pretty close, it should be all good. And just make sure your line of best fit at least touches all of the uncertainty bars. If it doesn't, you should try to redraw your line of best fit. Just rub it out. Try to redraw it because your line of best fit should ideally cross, if not at least touch through all of the uncertainty bars. You can see Now my line of best fit is at least scraping past these two bars, so that is still enough. All right, so part F. This is the final part. Using the line of best fit, find the value of the constant resistance globe. When you are analyzing any physics related graph, there are two things you can use to analyze the graph. One is the gradient. The second is the area. Always mentally note these two down. You either have to analyze the area or the gradient. It's very unlikely to ever be given the area to calculate in any experimental question. Right? You do have to calculate the area for your gravitational field graphs, but for the experimental questions, we normally use the gradient, something in the gradient, to tell us something about the experiment we're trying to find. In this case, we can find the resistance of the light globe, and that will sort of validate our experiment. All right, so let's have a think about this. What was the equation for our line of best fit? It was this, wasn't it? So R is equal to 24 over I minus big R. Okay, so in this case, let's have a think about this. What would the gradient tell me? Does the gradient relate to big R? In this case, it doesn't, right? In this case, the gradient relates to 24. It has a fixed value. So it's actually not my gradient that is important. It's related to the gradient, but it's my y-intercept that I have to find. So the y-intercept of this graph will give me my constant resistance light globe. And so I can just pinpoint this value. I try to approximate what it is around, at least try to get the answer around the ballpark. Right? And so then that will give me my value of R. So R is equal to, in this case, around 7.5 ohms, which is the resistance from the y-intercept of the graph. So actually, I completely forgot about the third aspect of the graph that you can analyze, which is the y-intercept. Or I should just say, oh, it is the y-intercept, not the, you can't analyze the x-intercept. Yeah, that is the y-intercept. From the y-intercept. Alright guys, so that just about wraps it up. So hopefully you guys didn't sleep through this video. Hopefully you actually paid attention to some parts. At least hopefully you guys got some tips, some advice from me running through this exam. Just you know, good luck guys for your actual exam, and make sure to carry on with the structure of the exam in sort of a similar way to as I've done it. I'm not saying this is the best way to do it, but I personally prefer this way, just going through the short answer section first, and then the MCQ, and then the remaining short answer section. That's just what works best for me, but I think that is the go-to way, in my honest opinion, especially from the feedback that I've gotten from a lot of other students who are also doing physics. That is the go-to way. You can skip the multiple choice section entirely and leave it to the end. A lot of times, a lot of people just they take the MCQ too lightly, to say the least. So they think they can just guess half of the MCQ, but guessing half of the MCQ will cost you a lot of marks, believe it or not.